Hello everyone, welcome to this tutorial. My name is Xarray. I'm a Google Earth Engine expert. In this tutorial, I'm going to show you how to calculate Aridity index. It's a climatological indicator that shows the degree of dryness based on precipitation and potential evapotranspiration with annual frequency. If you search about the Aridity index, there is a Wikipedia including a detailed instruction about the different method of calculations. However, the method based on the precipitation and potential ET is the most straightforward in the remote sensing data. And now I want to show you how to do this classification, how to calculate the index, and how to classify the output based on existing threshold. This tutorial is really useful for those of you who are interested to know more about the drought, about the Earth observation satellite data, and Google Earth Engine programming technique. Okay, if you want to learn how to do this procedure from scratch, let's follow this tutorial. First of all, we need to make a new notebook in the Colab environment and start importing library in the first step. We need to import the libraries allowing us to deal with the Earth Engine capabilities in the Colab environment, like EE library, GEE map library, and also we need Xarray library. The last but not least is the XE library. The XE library, as it is addressed in the previous tutorials, it is one of the newest libraries developed by the Google community, allowing us to bring Google Earth Engine data into Xarray format. In that case, we can apply Python scripts on the Google Earth Engine datasets and increases our capabilities and resources for the satellite data analysis. So now you can see the libraries imported and successfully installed and imported together. Then let's clear the output and establish a connection between Earth Engine and Colab using EE library. Start with authentication first and then initialize your Earth Engine account. Enter the project ID. If you already have an account in the Earth Engine, just go to the code editor environment. When you go to the code editor, in the upper right, there is an option. Go to project info and find your project ID. So let's copy the project ID into your code, just like that. The next argument is about the OPT URL. If you search about the Google Earth Engine and XE, you will find a GitHub address including a detailed instruction about how to use the XE. In this page, scroll down a bit and you will find OPT URL address like this. Copy and paste into the code. Let's run a cell. Now, Colab asking permission to access to your Earth Engine account. Click on Allow and select the account. Now permission granted. Click on Continue then. As you can see, from now on, we can actually have access to the Earth Engine resources such as data catalog and functions through the Python scripts. So, before further analysis, we need to set the region of interest, create a variable from GEE map, make a variable called the map function with the satellite base map, just like that. Let's run the map again. Now we have a user interface, including the drawing tools to select the region of interest. In this tutorial, I'm gonna select part of my country, northern Iran, where we have severe drought impacts over the last recent decades. Rectangle tools available. I wanna select northern Iran, where we have vegetation cover. Because if you back to the aridity index here, you can see it's based on the precipitation and potential evapotranspiration. And evapotranspiration actually calculating for those areas covered by the vegetation cover. That's important, your region of interest covered by the vegetation cover. So that's why I'm selecting northern Iran, where we have a dense vegetation cover close to the coastline areas. So back to the analysis here. Now we need to have the rectangle as a variable in the code because we need to filter our data based on the region of interest. ROI from the map, select the last feature, convert it to a geometry format. So let's run. As you can see, the ROI is available as a polygon here. So in the next step, we need to call evapotranspiration like this, TerraNet evapotranspiration, gap fill at 80 days, and also the precipitation data. These two data sets are available in the Earth engine, and I want to call them one by one and convert them into the annual formats. So let's start with the precipitation data set. Make a variable for GPM data set. So now you need to copy the collection snippet first and define or make a filter date. So make a variable like time start Earth engine dot date. So the data available, for example, since 2005 to 2025 ee.date 2025. There you go. So the filter date is going to show us the precipitation data from time start to time end. Let's select the target band. As you can see here, there are different bands available. The precipitation is the targets. We need to have the precipitation data. This is the monthly precipitation measurement, but the unit of measurement is millimeter per hour. We need to convert it to millimeter per month. There is a constant value, 730. It's the constant value to convert from millimeter per hour to millimeter per month. So it's really easy to do. Just make a loop structure and temporary function like lambda. Each input considered as a x. Now x dot multiply to the scale factor 730 is a scale factor allowing us to convert millimeter per hour to millimeter per month. Remember to keep the properties from input for the output image. So let's do the copy properties x and system time start, just like this, meaning that among the all input properties, I need to keep the system time start or the data acquisition because my analysis depends on the data acquisition. It's based on the time series data. So that's why I have to keep the time series for the further analysis. Okay, let's make a print to make sure everything's fine. GPM including 240 elements over 25 years, over 20 years, sorry. For each date, we have precipitation with the system time start. So now in the next step, we need to do the same process, but this time for the net evapotranspiration data. The evapotranspiration data including potential ET and actual ET, and there is a scale factor 0.1. So let's copy the collection snippet and make a new variable for potential ET. The modis, make a tuple, the collection snippet, paste it here. So make a filter date based on time start and time end. So as you can see here, we also have different bands, but PET or potential ET is the target one. Potential ET is selected. Remember to apply the scale factor 0.1. Make a loop structure again, and we need to have a function like lambda each input to the lambda is x multiply to 0.1 as a scale factor. Remember to copy the properties from input to the output again. Among the properties, as I mentioned earlier, system time start is the main one because we need to keep the data acquisition for the time series analysis in the next step. So now here, let's make a print to see how many precipitation data is available. As you can see, over 900 evapotranspiration data set is available because its temporal frequency is based on 8 days. Remember that for the sake of the aridity index, we need to convert these two data sets into the annual format. One of them has monthly frequency and another one has 8 days frequency. So now we can convert them into the annual frequency very easy and without any challenge. As you can see, time start and time end already defined. We need to calculate the differences between time end and time start. So here a variable time difference sets to from time end calculate the differences to the time start based on year unit of measurement converted into the round format. So now I want to have a time list including the years from 2005 to 2025. Make a list of sequence first. The list is starting from 0 and ends to the number calculated by the difference. So as we are starting from 0, it is important to subtract by 1, just like that. Make a loop structure. Now we want to add the date information into the list. So make a function lambda from time start go advance by x interval and year. What is the year x interval? The numbers available in the list of sequence. I want to go forward step by step based on x and year unit of measurement. So now let's make a print from a time list. A time list now is a list with 20 elements because we have 20 years difference from time start to time end. So as you can see here, the list is starting from 2005 and ends to 2024, meaning that we have a list of dates, and in the next step, I'm gonna calculate the sum of the precipitation and sum of the evapotranspiration per each year completely. So now we need a function to calculate the sum of these two parameters based on a list. So make a new function. For example, the annual function is, there are two arguments or two inputs for the annual function. The first is a date list. It's already defined. And another one is the collection. We have the collection and we have the time list. Okay. Now we need to start. We need to define a start date and end date for each year separately. So start date sets to ee.date, get the input date as a date format. End date, from a start date for each year, go advance to the next year, just like that. So now we need to get the annual image. The input collection now filtered based on a start and end of year or each year. Calculate the sum. Remember that whenever you are dealing with precipitation and evapotranspiration, it is important to convert them into the when you want to convert them into the annual format, it is important to get the sum of these values, not the average, because we want to see how much precipitation per year and how much evapotranspiration per year. So the function returning the sum image with a new system time start. The system time start will be defined based on a new system start date with millisecond format. Okay, The annual is a raw function. We need to apply it on the GPM and modis product. Okay, GPM annual sets to make an image collection format first, bring the time list first inside the image collection, make a loop structure using lambda, each date from the time list entered to the annual function x, and collection is GPM here. Print GPM annually. Let's run. Here we have 20 elements. We have an image collection that's showing the sum of the precipitation with the new system time start. GPM converted. Let's do the same for the modis data. Again, make an image collection format, get the time list, add a loop structure, bring it, consider it as x in the function, and apply the annual on the modis data. So the modis annual, let's run. The same output for the modis. Here we have the sum of the potential evapotranspiration with the new system time start. So, but still there is a problem. We have two image collections. They are separated with the same temporal frequency. I need to bring them into a same collection. For each year, we need to have two bands, one potential ET and another one precipitation. So the final collection will be like that. So the GPM annual dot combine the modis annual. Let's make a print. You can see again same result returned, 20 elements, but this time we have two bands, precipitation and potential ET for same year, repeating for every year separately. So everything's going well so far, but now we need to bring this data set into an Xarray format. In the Xarray format, we have several resources for the visualization and also doing extra analysis. And dataset sets to from the XR called the open dataset. The input is the collection, and engine sets to EE, coordinate system EPSG 4326. This is a unique ID for WGS84 that is same in all around the world. The scale should be 10 kilometer. Remember that here we have a data set with 10 kilometer and another one with 500 meter. It is important to upsample the 500 meter to the 10 kilometer because we need to have a same geometrical structure for our inputs. So we cannot do the analysis while they have different pixel sizes. So another argument is the geometry. Sets to the ROI. Let's run. So make a new code, a new data set created. Here we have a multi-dimensional structure. There are two variables, precipitation and evapotranspiration. So as you can see, they have values in 3 dimensions: time, longitude, and latitude. So here, and this data set is available. This should be available from 2005 to 2025, but something's wrong here. So as you can see, the time order is not right. So we need to sort it by temporal dimension. And remember that if you multiply to 1, nothing will be changed, but a new dataset created that is not connected to the previous one. This is a kind of trick. Without any scientific reason, it increases the speed of processing for the next steps. So let's run a dataset. Okay, check it out again. As you can see here, now the temporal frequency, actually the temporal uh, sequence actually ordered well, and it started from 2005 to 2025. Okay, everything's fine now, and we can calculate the aridity index. If you back to the website, the Wikipedia, there you can see the equation, a ratio between annual precipitation and potential ET. Now we have the annual ET, potential ET, and annual precipitation. So the aridity index, its calculation will be really easy. Just get the total precipitation or precipitation band over ds dot PET, just like that. The aridity calculated. Now we need to make a plot for each year. We have 20 times 20 image, 20 aridity map, and we need to make a multi-temporal map thanks to the Xarray visualization tools. So get the aridity data and make a plot like this. It is better to make a contour F format for the output visualization. X-axis belongs to the longitude, y-axis latitude, temporal axis time. Call wrap means how many map do we have, should we have per each row. So we have 20 maps. I think 5 is enough. If we have 5 map per each row is a good for visualization. Robust sets to true, increases the contrast for the output, and it is necessary. So, and levels, the levels is for the visualization, increases the legend levels that help us to see the differences easier. When you increase the levels, you will have more details in the output about the range of value, range of colors, and the differences between different classes. So, and the next parameter will be the color map. C map sets to turbo R, for example. Let's run. There you go. As you can see, now we have aridity map for 20 years, and the values ranges from 0 to 0.5. So based on Wikipedia sources, here you can see the output ranges in the true range of values. So meaning that the calculation is correct. And even we can do the classification to get a better information. As you can see, the lower values in the output shows hyperarid situation, means the area tends to the hyperaridity, and higher values tends to the more moisture or wetness, or finally we will have dry subhumid. If you search on the net and the papers, you will find the different classification for the result interpretation. It's totally up to you which one of them will be used. So now here you can see for some of the years the amount of the aridity increased, but for another years you can see the amount of the aridity decreased. It depends on the situation, the amount of the precipitation. For example, if we have enough precipitation, for example, like 2018 and 2019, the aridity index will have the higher value that shows we have low aridity conditions. But if we have a lack of enough precipitation for each year, such as 2021 here, you will see the lower values in our region of interest, or 2008, meaning that we have a higher aridity in our region of interest. Or you can see the coastal areas located in the northern Iran always actually having a good situation and there is no serious problem in these areas. But in the dry years, you can see even in the coastal areas, the rate of aridity also increased, meaning that the aridity can also have impact on the, for example, areas close to the coastline with the enough precipitation per year. It causes PR reduction, even in this region, and also may have negative impact even in longer period of time. So now if you want to save the output, remember to input or import matplotlib.pyplot as plt. So, and now the matplotlib help us to save the fig with a name. For example, this is aridity map with PNG format, DPI 360. And in addition to the DPI, what else do we have here? BB box inches. Sets to tight. Let's run and go to the left panel. Here, as you can see, the Aridity map is ready to download. Just click on download. After a few moments, the download process started, and you will have a high quality map that shows the multi-temporal aridity variation in the region of interest. So, and in the next step, or the final step, I want to show you how to do the classification, such as the previous example. At the end, you can use the Xarray structure for aridity classification. And also it helps you easier way to interpret the results. So now we have aridity map, for example, from Xarray. Where is a useful function to set the different threshold in the image. So, for example, the first condition is aridity values less than 0.5. So, in the aridity map, values less than 0.05. So we set, for example, class number 1, aridity. Now it's right. Okay, we set 1 for values lower than 0.05. Okay, sets 1 and okay, the rest of the values will have a new condition. So again, Xarray. This time we want to say that pixels between or pixel values between 0.05 and 0.2 is an arid class. So we already settled the first condition, and these values from 0 to this value already selected. Now we can set a condition for the values after the first condition. So meaning that it's really easy. Just we can say, okay, now just pixels less than 0.2, because already we actually settled a class for the values from 0 to 0.05. So the second condition considered values greater than the first to the 0.2. So we set class number 2 for the aridity class. So for the rest of the pixels, we are doing the same process. Now pixels less than 0.5 greater than 0.2. The pixels lower than 0.2 already addressed. Now we want to have pixels aridity lower than 0.5 with class number 3. So, and again, pixels aridity less than 0.7, for example, 0.7 or less than 1, for example, here. we want to actually label them with value number 4, and the remained pixel will be unknown. So numpys, it's not defined already, so we need to import numpys as np. So let's run, and Aridity map is ready. Okay, let's call the Aridity map in a plot format. So x sets to longitude dimension, y sets to latitude dimension, call sets to time, call wrap 5, and the next one, for example, here is no need to the turbo anymore here. Let's run. So as you can see here, we have a classified situation. If you want to have a particular color for each class, I'm suggesting to use the contour format. So contour F. So there you go. You will have a particular color for each range of values. But the color of values are really close to each other. We can use the different color palettes. For example, here I can use the, for example, turbo again. Now you can see, for example, values class number 2, the arid areas, pixel values between these range of values actually showing with this color, and areas with very high values showing with the dark blue color. So now it's easier to interpret the result, as you can see here. So for example, we can check these areas in the first image. For example, these areas in the first image showing values around 0.3, that should be semi-arid area, the class number 3. Yes, the class number 3. This color is class number 3. So now it is easier for the interpretation when we do a comparison with the original image. So now you can see here we have different classes: hyperarid, arid, and semi-arid, and dry subhumid. So as you saw that we made a map for the aridity index, and I hope you like it as much as I do. Please try to use this tutorial for different region of interest and assess the index performance and see how it works, and share this tutorial with other remote sensing fans in all around the world. If you faced with any challenge about this tutorial, the code example available below this video on my YouTube channel. If the problem still exists, feel free to reach me out and put your comments on my channel. Thank you for your attention.